All right, so the first example we're going to look at is that where we have a coil of wire here, and it's within a magnetic field. And this is actually a 100-loop coil, right? It has a side length of 5 centimeters, and we see the magnetic field here, in this case, is pointing into the page. It has a value of the magnetic field of 0.6 Teslas. The wire itself has a total resistance of 100 ohms, and what we're going to see is that it's quickly pulled from the field at a constant velocity. So at time equals 0, that's the position of the image, and then it takes 0.1 seconds for the whole coil to reach the field-free region. Right, so someone's going to have some external force and they're going to pull it to the right, and this entire coil is going to be removed from this magnetic field into this region here where the magnetic field is 0 in 1/10 of a second. So the first thing that we're going to look at is the rate of change in flux through one loop of the coil. Now, if we look down here, so here's kind of our approach. We're going to start by finding how the magnetic flux changes during the time interval, and then we're going to use the ideas of Faraday's law, gives the induced EMF, and the Ohm's law then is going to produce the current, because later on it asks us what is the total EMF and the current induced in the 100-loop coil, and how much energy is dissipated, and then what is the average force required. So what's this force here? So how would we complete A? So again, in A, we're going to find the change in flux. So what we need to understand is that we have two fluxes, an initial flux, which is going to be BA cosine of 0. And so this value goes to 1, and that's just going to be BA. And then we have a final flux, and that's actually going to be 0, because our loop is going to be removed from the magnetic field. B would go to 0, and so our flux would go to 0. So our change in flux over our change in time is going to equal flux final minus flux initial over our time. That's then going to give us 0 minus BA over time. Which then is going to be B times our area would be our length squared over time. Working through that then, we're going to get a change in flux of negative. Oh, yep, we should put our negative in there. Negative 1.5 times 10 to the negative 2 Webers per second. So that's the rate of change. So the key word there is the rate of change in flux, right? So that's how we're going to get that value there. Some key things in solving this. Magnetic field is already set up in the units that we need. Our length, we need to make sure we convert this to meters when you plug that in there, and then time obviously is set up appropriately for us as well. The next thing that we'll do is we'll work through B, which is going to first find the EMF, and then the current in the wire. And so to find the EMF, we're going to use Faraday's law, which EMF is equal to a negative N, which is my number of loops, and then that rate of change, which we found earlier, which is our change in flux over time. So we already found this value earlier, and so we're simply going to multiply that by 100. So we have negative 100 times negative 1.5 times 10 to the negative 2 Webers per second. Webers WB per second. And so my EMF is going to be 1.5 volts. So I'm going to have a 1.5 volts pushing the electrons around that. And then the next thing I can do is I can look at my current. I can use Ohm's law, which is V equals IR. If I'm trying to solve for current, I can just move it to I equals V over R. And then I have 1.5 volts divided by a total resistance of 100 ohms within my circuit. And I should get a current of move this 2 places, 0.015 amps within my circuit. So there's my EMF, and there is my current that's going to be moving through. Now, as we're looking at this, we can try to understand what is happening and what is the direction of the current, right? So if we look at here, our flux is going to be decreasing because we are moving out of this magnetic field. So to counteract that, the current induced in this coil is going to produce a magnetic field which is going to match the direction of the existing magnetic field. So my B induced would point in the direction, and it would be in here, right? So that this would be a better place to put it. B induced would point in that direction. I'm going to point my thumb into the page. I'm going to wrap my fingers around, and I'm going to get that the current is going to flow, in this case, in a clockwise direction around my loop. The next part then asks for the energy which is dissipated or energy that is lost within my coil. And so remember that power is energy per second. And so we can then say that our energy is going to be our power times the time which is going to be produced, because that's going to be joules per second multiplied by seconds, and so my resulting units would just be joules, because seconds then here would obviously be canceled out. So to do that, I'm going to have my power, which again is current times, voltage, or resistance squared, or however you want to identify that. And then obviously we're going to have that by time. So energy is going to equal I times V times T. So we would have 0.015 times 1.5 times 0.1 for the time that it took for that to be produced. And from that, I'm going to get an energy that is dissipated as 2.25 times 10 to the negative 3 joules. So that's how much energy I have lost within my wire as it moves from this location outwards. Now, the last part of this problem asks us to find the average force required to remove the coil, or F external. And if we look at this, we remember that it talks about a constant speed of which it is removed. So if we think about the force diagram in this case, we have force external, and then we also are going to have some other force magnetic pointing back this way, because we need a constant velocity. Means that acceleration is 0, which means F net as well is 0. So a few ways that we can go about this last part. One way is the work energy theorem, in that if I lost a certain amount of energy within my coil, then I must have done a certain amount of work as well. So we can say that the work is force times distance. The distance which this coil moved, once the coil's up here, it's just going to be here. So the total distance that this part of this coil would have moved to there is simply the length of that one side. So if we're looking then for the force, my force then would be equal to my work divided by my distance. The work is what we solved from the previous slide, and so my work is 2.25 times 10 to the negative third joules divided by the distance, which is 0.05 meters, and I would get an external force, which is going to equal 0.0450 newtons. So that would be the force that I would need to pull that wire to get it from here to here in 1/10 of a second, moving at a constant speed. Lastly, we'll go through an alternative way of which we can solve for D. Again, remember, D is asking us to solve for the average force required of the external. And like we had said previously, that force, because it's moving at a constant velocity, must equal an additional force pointing in the opposite direction. So here's my external force, and then here's my force of magnetic field. And the reason we can say that is because we've already said that the current in this coil is going to be pointing in a clockwise direction. So we can use the force on a wire, on a current carrying wire, which is F equals BIL, to help us figure out what this external force would be. Now, what we can think about is the force. You would use your right-hand rule. Your thumb should point in the direction of the current flow. Your finger should point in the direction of the magnetic field. So at the top, I would point my fingers into the page, and I would point my thumb to the right, and I would get a force. Whoa, that was weird. I would get a force that would be pointing upwards like this, based on the top of my loop. At the bottom of my loop, my thumb would be pointing to the left, so I'd get a force that would be pointing this way. Those two forces, though, are going to cancel each other out. On the left-hand side, I would point my thumb upwards, and I would get this magnetic force right here. We will say that there's really no magnetic force here because very quickly that part of my coil is going to be leaving the magnetic field. So there would be no magnetic force pushing on this one due to the fact that there is no magnetic field that it is experiencing. So what we can say is we can say that F magnetic, which is BIL, equals force external. And again, we know that because we're moving at a constant speed. So F net equals 0, acceleration equals 0, which produces a constant velocity, right? Object in motion stays in motion. So if we were to solve for this, my magnetic field is 0.6. My current we already solved for is 0.015. And then the length is the 5 centimeters, again, 0.05 meters. That all multiplied together is going to get me, one other thing. We're going to multiply that by 100 because we have 100 coils. So this is my number of coils. If I just had one coil, it would just be the BIL. But because we have 100, we're going to multiply that by 100 as well. And so with that, we're also going to get I'll write it down here, 0.0450 newtons. And what we can see is that value here is the exact same value that we got previously, showing that both of those methods are going to give us a correct result for that external force.